All glory and honor belongs to the Lord. We ask you, Almighty Father, to grant us good class this evening. Give us the ability to learn and understand what we've seen and what we have done and what we are going to share together. This is our prayer in Jesus' name.
Amen.
Okay. And last week we talked about exploratory data analysis. So because it was more like what do you call it? It proves. We're reading the text as a prose. It's like a novel. So we couldn't understand what most of those analysis meant. So I decided to write out a note and included something that's going to explain that we can see a graphic, a symbol, something to represent what we are talking about. All right, the first thing we talked in exploratory data analysis, whenever we are doing analysis, we always have what we call histogram. So the histogram, each column of the histogram is called a beam. I said it last week. This is how a histogram looks like. Let me see if I can increase the font size. All right, this is how a histogram looks like. So these figures are arbitrary figures. So they are just assumed figures ranging. They have different ranges, 1 to 5, 5 to 9, 9 to 13, 13 to 17, 17 to 21, and 21 to 25. Each of them has a what do you call it, four units in between, because between 1 and 5,
It's
5
4
minus 1 is 4, 9 minus 5 is 4. So the ranges are 4 units. So this is a typical histogram. So whenever a data, were you there when I explained a univariate, difference between a univariate?
No, I wasn't there. I wasn't there.
All right. A univariate data analysis has to do with, a typical example is, let me give an example. If you collect the data from one population, let's say only Uyo, or if it is one school, only that school, or if it is a local government, only that local government.
Okay.
Much of the analysis will be univariate analysis. But if you obtain data using the same, is it parameter? Yeah, using the same parameters.
Yes, parameter.
And you obtain the data from different locations, samples from different locations. In fact, if it is 2 different locations, two different samples or two different populations, you apply bivariate. If it is more than two, you apply multivariate. You understand now?
Multivariate.
Yes.
And bivariate. If it is two, it's bivariate.
Yeah,
it's more than two. It's
yeah.
Okay.
Multivariate. But if it is one population or one sample, it is univariate analysis that you will do. Okay. The reason we do bivariate and multivariate is that there will always be what we call some comparison kind of test. Sometimes we'll have correlation, we'll have other kind of analysis that requires different data. We can have test of independence to check if this one is independent of this other one. We can have different kind of tests, comparison tests like that. So if it is one data, there is no need for comparison test. There is no need for cross variation. So you may not have all those, how do you call it, correlation and the rest of them. So univariate analysis are few. We have the histogram. You know, we talked about the basic ones, the basic parameters that has to do with the mean, the variance, the range, and the rest of them. Yeah, now we are talking about representation. Yes. How you can represent the data for somebody to see and understand what you are talking. Because most people don't know how to read numbers. But if you can show them as a graphic method, they will understand. So this is how histogram looks like. With this histogram, like these ranges, you can use it to explain age range. You can say children that are 1 to 5 years old, children that are 5 to 9 years old, 9 to 13 years old, 13 to 17 years old, 17 to 21 years old, and 21 to 25 years old. While this y-axis has to do with the number, that is the frequency. So children that are 1 to 5 years old might be only 5. Then children that are 5 to 9 years old might be about 11. Children that are 9 to 13 years old might be 26. Sorry, 23.
23.
Yeah. Then children that might be 13 to 17 years old might be 24. Children that are 17 to 21. Yeah, that is 9. Yeah. Children that are 21 to 25. That is 4. I hope you understand.
Yes, please.
That's how histogram works with univariate. Another population that you can use histogram is the bivariate. But once it gets to multivariate, if you use histogram, it's going to make the people might get confused.
Okay.
Yeah, because in the case of bivariate, you might say if this population, this one is the first population, then you have a second population. If you want to combine, you can just change the color. The first population might be blue, second population might be green. Are you getting me?
Yes. And that means we are no more using histogram.
No, you use, as if you want to use histogram, it's mostly good to use for univariate and bivariate.
Bivariate, yes.
So, like this one is univariate, but if you want to do for bivariate, after drawing, this is the first population. Then the second population, you might change the color. to
Okay.
win. Understand?
Okay. Yes.
From there, you now start comparing this population and this other population. Are you getting me? But
Yes,
once
please.
it is more than that, and you have so many histogram describing the same thing, understand? It becomes confusing to the person you are trying to explain the data. Understand?
Yes,
So
please.
normally histogram is always good for univariate and bivariate cases. Highest three population also. You want to compare three populations. All right, we have the stem and leaf plot. I think this is one of the reasons I decided to draft this note, this stem and leaf plot, because it was difficult to explain.
Okay.
You are collecting, especially you are collecting how do I call integer data, not um, not continuous data.
Not continuous data.
Especially you are collecting integer data in a bivariate, sorry, in a univariate population. Understand? You are
Okay.
collecting integer samples. Stem and leaf plot is very, very beautiful. Understand?
Okay.
Or if it is more than that, it is no longer beautiful. This is how it works. Supposing you collect the number, you met how many people? You met a group of people in the bank and you want to get their age. And the first person you sample, you say, okay, I want to sample 1, 2, 3, 4, 5, 6, 7, 8. 8 people, I want to sample their ages out of everybody that is in the bank. And you met the first person after your random first person says he's 23 years old. Random second person says he's 35. Random third person says he's 27. Random fourth person says 45. The next 33, then 38, then 40. How you represent this? You know, if you start writing this thing on paper, supposing you want to collect up to 100 integer of data, it will become cumbersome.
Yes.
So this is where stem and leaf plot comes in. It's like an abacus. Understand? So instead of you duplicating and rewriting the data, you can just create a table that has to do with the first digit of the integers. Now, our lowest integer is 2. Then we have 3. Then we have the highest integer, which is 4, as in first digit of the integer. That's what I'm talking about too. You understand?
Yes.
Now, every other numbers follows. The first person was 23 years old. So you now write 3. Second person was 35. You go under 3 and write 5. Third person was 27. You go back to the one that you add 22 as a first integer and you write 7. You understand now?
Yes.
Now, the next person is 45. You go to where you have 4 and write 5. Then the next person is 33. Then you go to where you have 3 and write 3 here. Then the next person is 38. Then you come and write 8 here. Then the next person is 40. Now put 0. You can now rearrange by bringing, like this 45, you might bring the 0 to the front and bring the 5 to the other side.
Yes.
After you are done, you can rearrange. Like this one, 8 is the highest. Then will be 5. You bring in 5 here, and you bring 3 here. You understand now? So when
Yes.
you now rearrange, it comes out beautifully. So if you collect integer data up to 1000, and you discover that most of them are repetition, so you just arrange them like this. So even if 3 people have 22, you now have 2, 2, 2, 2, 2. You understand? Then the next number follows. After collecting, then you rearrange, and that is how it looks like. So this is how stem and leaf plot works. So then there is another one called.
And is that all about that?
Eh?
Is that all about that?
That's all about stem and leaf plot.
It looks simple.
Yeah, it's a way of, it's graphical, it's a presentation of data.
I think I prefer it to histogram, sir.
So you collect the group of data, you want to make it simple for people to understand. Bring it out. That's in people, the first person was 23 years old, then we have 27 years old, we have 33, we have 35, we have 38. You get it? You can even color each of the boxes. You can add color so that somebody will easily understand that this is what you were trying to do. You understand me?
Yes.
I add color like blue here. So that's it. So that is for the stem and leaf plots. It works like an abacus, using arranging data, large number of integers. Just arrange them very easily.
Very easy.
All right. Another one is a box plot. Box plot is another thing that you will see when you are doing analysis and you are asked to present your data, or you saw an analysis somebody did and you want to understand. A box plot takes care of 3 points: the minimum, the first quarter, and the third quarter, then the maximum. The minimum is the lowest, that is the pay. Then you look out for the first quarter, the median, which is the third quarter, and the maximum. So those ones are calculated. There is a way to calculate it, but you can just do it with the computer. And even if you have a group of data and go to the computer and generate a box plot, it will give you this. But we are not doing the calculation. What we are doing is to understand how data are represented. So if it has to do with age, once you see a box plot like this is a box plot in an horizontal way. Normally, it's always kept vertically. But they are putting it horizontally so that somebody will really understand how this thing came about. Now, you find the median of the age. It forms your middle. The first quarter forms the age of the plot, and the third quarter forms the other age of the plot. Then you have the minimum, the other side, you have the maximum there. Then you now put it upwards, that is vertically. So you can use a box plot to represent several populations or several samples. You understand?
Mm.
Several samples. A box plot is one thing you can use as many samples. That is why you always see box plots in many tedious analysis. The reason they do it is it helps them to understand the minimum, as in the first quarter, middle age, in case of age, as the middle data and the maximum data. So you just arrange them. So it easily explains the behavior of a particular population as compared to other populations. So you can arrange as many populations using the box plot. So somebody will say, okay, this population, this is the maximum data, this is the middle data, and this other population, this is that. I hope you understand.
Yes, please.
So then the next, we have the QQ plot. The QQ means quanta.
Contact.
Yeah. So we have the, when it is plotted against the normal distribution or a normal population, it is called quanta normal. Either a normal plotted against a normal distribution or plotted against a population that is already known to be a normally distributed. You understand?
Mm.
It will now become QN, quanta normal.
Okay.
But when you do not know if the populations, any of the populations, if you don't know if they are normally distributed, if you want to compare the two populations, you now do quanta plot. So that's it. I didn't put out a graph for the quanta plot, but you obtain the same minimum first quarter, median, third quarter, and maximum of each of the population. Then you now compare. If it gives you a straight line graph or almost a straight line graph, you know that the two populations are from the same distribution. Okay. But if they vary, which means they are not from the same distribution, if they don't give you a straight line, if you plot this population against this population or this sample against this sample, understand? If they don't give you a straight line, you know that there's something wrong, that they are not from the same distribution. So you now look for their the distribution for each of the sample. So that is how it is used. You may not be, as in, it is not like, okay, you are given a population, find if they are same population. No. When you are working with data from different populations, this is a way to check whether your samples, the data you collected, you have collected the correct samples. Because once they don't follow a straight line, it means that your samples, the two samples are different. You are obtaining them using different parameters. You are not really following the same strategy. You understand now?
Okay.
So you use a way such that you are able to obtain the data. When you obtain the same way, use it to obtain the data in another population, the same way using updating data in another population. By that, you should be able to obtain same distribution. So if somebody obtained the data for you, you should use this quarter plot to check if the data can be said to be the same. If they follow almost a straight line, which means they are of the same distribution. I hope you understand.
Yes, please. You
So
said if we use it to check in case somebody obtained data for me,
yeah,
so
yeah,
I should use quantum quartile plot to
yes,
check. And
yeah.
if
Not
obtain,
necessarily somebody obtain for you. Any
okay,
data, as I
that is
want to
two
check if they
population.
are the same distribution.
Okay.
So this is what you use.
So once I
Remember,
can get straight line, it
yes,
means they are
or
the same.
almost a straight line.
Mm.
You know that they have a similar distribution.
Okay.
Yes.
What if they
So
are against each other?
if they don't follow a straight line,
Mm.
then it is another distribution.
Another
You know,
distribution.
each distribution has a shape. We have the
Yes.
logistics and the same. So you check the shape
Okay.
and check other distribution.
Okay.
You browse
Okay.
shape of other distributions and check from there to give you an insight of what was wrong. And probably if you actually wanted to get a specific distribution, you now either change the data, get another one, or if you want to continue, you can continue with that distribution, knowing that it is not the same
The same
distribution with this
distribution.
other one. So it is in experimental design, they are not conclusive. It depends on what you want. I told you it's like a building plan. You
Yes.
design what you want. So, but the parameters, the randomization must be there. It has to be designed to accommodate.
Okay.
Yeah. So that's it. We won't go into the calculation, but the thing is, this will help us to interpret whenever we say analysis. We understand what the
Yes.
person was trying to do, and we are able to read it to the understanding of some other person or to our own understanding.
Mm.
So going back to our text, that was let me see. Let me see. Okay, this is the text we're using. So that we can see what next we are going to discuss. May not be tonight. All right. Okay. All right. This is the stem and leaf plots, which I just explained.
Yeah.
Then the box plot. This is how the box plot is. The minimum, the first quarter, the middle quarter, that is a median. Then the third quarter, then you have a maximum. So this is, supposing you collected a sample from, okay, you want to collect samples from like 5 schools in Uyo. So in the first school, after obtaining the samples, decide to represent them as a box plot. Then you obtain from other sample, you represent it as a box plot. I think the idea is to help whoever you want to explain to understand that this is the lowest, this is the first quarter, this is the median, this is the third quarter, and this is the highest of this data. This other data, this is it. This other data, this is it. You understand now?
Yes, please.
So it's very, very useful to represent populations. So whenever you see box plot, that is how you read it. Have you seen here?
Yes.
So that is it. I think we'll continue. Next class, the quarter quantile normal plot. We won't go into calculation. This calculation is very tedious. You just data, you just, when you are running analysis, you just use the computer as a computer to give you this, and this, which we will definitely get to that in future. This is a simple example of 2 different data. This is the expected normal value and what was observed. So the person is comparing the data to see if they have the same distribution. So if you see this other one, see how they have curved. They are not in the same distribution. They are not in the same. See, this one is scattered too. They are not in the same distribution. So this one is close. So, all right, we'll talk about multivariate tomorrow. Good night.
Good night.
Night rest. We ask God to bless this our class and whatever we've learned in Jesus' name.
Amen. Thank you.
You're welcome.